Tor Lacey here with a lecture on interpreting geologic history. We are going to apply what we've learned about geologic structures and interpreting block diagrams to sorting out the chronological sequence of events that have happened over geologic time to create the geology we observe today. Our learning outcomes include appreciate the magnitude of geologic time and chronologically arrange major geologic and biologic events in Earth's history, interpret a sequence of geologic events and unconformities from geologic cross-sections using relative dating principles, understand the significance of the age of Earth, and be able to list the geologic periods and eras of the Phanerozoic eon and relate significant geologic and/or biologic events to each. And finally, create a geologic map. In order to interpret the geologic history of any given area, we need to identify the rock units and the structure of these geologic bodies. This entails making a geologic map of that area, from which we can construct geologic block diagrams, which you learned about as part of the lesson on geologic structures. From the three-dimensional block diagrams, we can interpret the structure and the relationship among the geologic bodies. This, in turn, allows us to interpret a fourth dimension, geologic time. Earth is 4.6 billion years old. This is an inconceivably large amount of time. To try to put this in perspective, consider a calendar year, with Earth's beginning at the beginning of that year and today at the end. On such a timeline, 100 years would be equivalent to less than 1 second. Another way to look at it is to consider it visually, such as we have in this illustration here. As we spiral up from the beginning of Earth's history 4.6 billion years ago and get closer and closer today, and we come all the way up to here, at this time we are 90% of the way through. It wasn't until this time that life moves on to land. So consider that for 90% of Earth's history, there was nothing on land. Nothing green, nothing moving. It wasn't until we're 90% of the way through that life moves on to land and it begins to look like the Earth that we know today. If you think this stuff's interesting, then I would encourage you to take a look at this website here, which offers a very nice and I think easy to read summary of the evolution of life on Earth. And plus there's a video if you want to get into it in more detail. The main objective of this lesson, however, is to learn how to interpret the geologic history of a given area by arranging the geologic units in their correct chronological sequence. This is known as relative dating. For example, arrange the following events so they are in the correct chronological order relative to one another. Trump becomes president, World War II, today, dinosaurs go extinct, America's independence. So from oldest to youngest, we have dinosaurs go extinct, then America's independence, then World War II, then Donald Trump becomes president, and then today. So this does not require determining the exact time when these events happened, which is known as the numerical age or numerical date, but instead arranging events in their correct order relative to one another. This is done by using fundamental geologic principles, also known as relative dating principles. Examples include cross-cutting relations or original horizontality, which are for the most part based on common sense. Relative dating principles, original horizontality, and superposition. Sedimentary and extrusive igneous rocks form in more or less horizontal layers. Superposition describes that as a sequence of rock layers form, younger layers are always deposited atop older layers. These photographs offer some examples of this. We see the horizontal strata here. and horizontal layers of lava. So this is a reflection of the structure of the sediment and lava when it originally formed. Here we see superposition with the older layers below the younger layers. These layers here needed to have been present in order for the younger stuff to be deposited on top of them. Original horizontality is especially helpful when we are discerning structure. We know that the layers needed to have been horizontal to begin with, but if they are no longer horizontal, we can reasonably conclude that deformation has happened. The principle of cross-cutting relationships. The rock unit that cuts is younger. A rock unit or structure that cuts through another rock body is always younger than that rock body that it's cutting. So the oldest unit is the main rock here, let's call that granite, which is being cut by two dikes here. This granite needed to have been present in order for these rock bodies to cut through it, so therefore they are younger. Principle of inclusions. Rock particles contained within another rock are always older than the surrounding rock body. The included fragments are older. So a couple examples here. Let's call this younger rock body here granite, which is including the older rock that's quite dark that are called xenoliths. So the granite rose up as magma into the pre-existing darker rock body. Some of those pieces broke off into that magma, and then the magma solidified around them. Here's a sedimentary rock. These fragments here needed to have existed first in order for the other sediment to be deposited and cementing around it. So again, the fragments are older. Unconformities. Unconformities form when deposition of sediment stops, erosion removes sediment and rock, then deposition resumes. This cycle may take tens of millions of years, removing tens of millions of years of rock record, and therefore tens of millions of years of geologic time. So unconformities represent a gap in the rock record, missing geologic time. And there are three types of unconformities. An angular unconformity may form in this way. Step 1, mountains form and layers fold, then erosion removes the highlands. So erosion removes the higher elevated area, exposing the folded layers. Environmental conditions change over time, maybe sea levels rise, and sediment is deposited atop those older folded layers. These layers are tilting at a different angle than the layers above, so we call it an angular unconformity. The wavy line represents the unconformity or erosional surface. Nonconformity. Again, let's go through the steps. So originally, furthest back in time, we have a situation where there was some sedimentary strata that had been intruded by magma rising from beneath, creating this structural juxtaposition here. Erosion removes the rock cover, so the crystalline rock is exposed at the Earth's surface, crystalline rock being the intrusive igneous rock that solidified from the magma. Now I've got the erosional surface. Again, environmental conditions change, perhaps sea levels rise, and then sediment is deposited on top of the intrusive igneous rock, which solidifies into sedimentary rock. And again, this wavy dark line represents our unconformity, in this case a nonconformity, because we have two different types of rocks in contact with one another on either side of the unconformity, igneous versus sedimentary rock. Disconformity. So further back in time, we have sedimentary layers beneath the sea. Sea levels drop, exposing those sedimentary rock layers on Earth's surface. Erosion removes some of the layers. With more time, sea levels rise, and deposition happens atop of that erosional surface. In this case, this is a disconformity, where sedimentary rock layers are separated by other sedimentary rock layers that have more or less the same dip or tilt, but there is an erosional surface between them. Disconformities can be the most challenging to notice in nature because the rock layers are tilting more or less the same above and below the unconformity. Let's look at one in real life here so you can see an example of this. Here we have horizontal strata that has been eroded, and we can see that with this subtle change here, which I highlighted with the purple. This may have happened because these layers were exposed to the Earth's surface. Perhaps a stream was flowing in this area, cutting down into the layers, and the stream dried up. Maybe a lake or sea levels rose in this area. Sediment was deposited atop the erosional surface, giving us the disconformity here. So with these relative dating principles, we can arrange a sequence of geologic units in their correct order from oldest to youngest. So let's consider this cross-section here. Which would be the oldest layer? Well, considering superposition and original horizontality, we could conclude that C would be the oldest unit. Imagine these layers tilted back to horizontal. C would be at the very bottom, and the oldest layers will be at the bottom according to superposition. So we put C, then G, then A, then I, then K, then F, and it looks like we have an erosional surface, an unconformity. In this case, this would be an angular unconformity. So then D would have been deposited on top of that erosional surface, followed by J, H, and B. So you'll be doing the same thing in your lab exercises. Good luck.